Electron capture is a process in which the proton-rich nucleus of an electrically neutral atom absorbs an inner atomic electron, usually from the K or L-electron shell. This process thereby changes a nuclear proton to a neutron and simultaneously causes the emission of an electron neutrino, P plus E minus N plus nu E. The daughter nuclide, if it is in an excited state, then transitions to its ground state. Usually, a gamma ray is emitted during this transition, but nuclear excitation may also take place by internal conversion. Following capture of an inner electron from the atom, an outer electron replaces the electron that was captured and one or more characteristic X-ray photons is emitted in this process. Electron capture sometimes also results in the Auger effect, where an electron is ejected from the atom's electron shell due to interactions between the atom's electrons in the process of seeking a lower energy electron state. Following electron capture, the atomic number is reduced by 1, the neutron number is increased by 1, and there is no change in atomic mass. Simple electron capture results in a neutral atom, since the loss of the electron in the electron shell is balanced by a loss of positive nuclear charge. However, a positive atomic ion may result from further Auger electron emission. Electron capture is an example of weak interaction, one of the four fundamental forces. Electron capture is the primary decay mode for isotopes with a relative superabundance of protons in the nucleus, but with insufficient energy difference between the isotope and its prospective daughter for the nuclide to decay by emitting a positron. Electron capture is always an alternate decay mode for radioactive isotopes that do not have sufficient energy to decay by positron emission. It is sometimes called inverse beta decay, though this term can also refer to the interaction of an electron antineutrino with a proton. If the energy difference between the parent atom and the daughter atom is less than 1.022 MeV, positron emission is forbidden as not enough decay energy is available to allow it, and thus electron capture is the sole decay mode. For example, rubidium-83 will decay to krypton-83 solely by electron capture. A free proton cannot normally be changed to a free neutron by this process. The proton and neutron must be part of a larger nucleus. History. The theory of electron capture was first discussed by Giancarlo Wick in a 1934 paper, and then developed by Hideki Yukawa and others. K-electron capture was first observed by Luis Alvarez, in vanadium-48. He reported it in a 1937 paper in Physical Review. Alvarez went on to study electron capture in gallium-67 and other nuclides. Reaction details. Examples. 2613 Al plus E minus 2612 megagrams plus nu E 5928 Ni plus E minus 5927 Co plus nu E 4019 K plus E minus 4018 Na plus nu E. The electron that is captured is one of the atom's own electrons, and not a new, incoming electron, as might be suggested by the way the above reactions are written. Radioactive isotopes that decay by pure electron capture can be inhibited from radioactive decay if they are fully ionized. It is hypothesized that such elements, if formed by the R process in exploding supernovae, are ejected fully ionized and so do not undergo radioactive decay as long as they do not encounter electrons in outer space. Anomalies in elemental distributions are thought to be partly a result of this effect on electron capture. Inverse decays can also be induced by full ionization. For instance, 163 Ho decays into 163 dy by electron capture. However, a fully ionized 163 dy decays into a bound state of 163 Ho by the process of bound state beta- decay. Chemical bonds can also affect the rate of electron capture to a small degree depending on the proximity of electrons to the nucleus. For example, in 7b, a difference of 0.9% has been observed between half-lives in metallic and insulating environments. This relatively large effect is due to the fact that beryllium is a small atom whose valence electrons are close to the nucleus, around the elements in the middle of the periodic table. Isotopes that are lighter than stable isotopes of the same element tend to decay through electron capture, while isotopes heavier than the stable ones decay by electron emission. Electron capture happens most often in the heavier neutron-deficient elements where the mass change is smallest, and positron emission isn't always possible. When the loss of mass in a nuclear reaction is greater than 0 but less than 2 meters, 0 to 1 e, the process cannot occur by positron emission but is spontaneous for electron capture. Common examples. Some common radioisotopes that decay by electron capture include. For a full list, see the table of nuclides.